Thank you. So I will give 3 tutorials. First 2 of them will be related to symmetric functions. So we will speak about symmetric polynomials in infinitely many variables, how to understand those, how to deal with those, and what are the formulas which are necessary for understanding some parts of the Alexei's course. Well, as the third lecture, the topic will be completely different. It will be more lecture showing some pictures. So I will try to give some examples of general formalism which will be explained by Alexei in his 4th lecture. So my third TA session will be exactly after, so it will be on Thursday, and I will show some applications to some very precise probability models, so we will be able to see what's actually happening in that probability models. Okay, so let's start with symmetric functions. So we have these handouts which summarize most of the formulas which you might need. So, well, okay. So let's start from basic definitions. We will speak about symmetric polynomials in infinitely many variables, but let's start from finite amount of variables. Microphone is not working? I don't know what to do with it. Maybe such way? No? Maybe this one. This one? All right. Yeah. Can you hear me now? Yeah, thank you. So take n variables, x1, xn. So consider symmetric polynomial in this variable. So we'll consider ring of all symmetric polynomials in variables x1, xn. So these are polynomials which are invariant under permutations of coordinates. For example, if you have just 2 variables, x1 and x2, then the symmetric polynomial is a polynomial of these 2 variables which satisfies very simple identity. Okay, so some simple examples of symmetric polynomials, again in 2 variables, are say sum of 2 variables, or maybe product of squares, or maybe, I don't know, x1 squared plus x2 squared. So not very complicated thing. Okay, what we will need some very specific symmetric polynomials. So these are so-called elementary symmetric functions, which are denoted by ek usually. Elementary symmetric functions. So what is it? So for finite collection of variables, it's a very simple thing. So ek is sum. So we have indices are from 1 to n, xe1 times xe2, xik. So what does it mean? Suppose that we have 3 variables. So n is equal to 3. Then there are only 3 elementary symmetric polynomials, which are e1, which is the sum of variables, and e2, which is the sum of products of variables, finally e3, which is the product of all variables. Okay, yes. For the sake of notations, we will say that 0th polynomial is just constant 1. Thank you. So there is a well-known theorem which is sometimes called fundamental theorem of theory of symmetric functions, which says the following. So let's denote this ring of symmetric functions in n variables by lambda n. Then fundamental theorem tells that this lambda n is isomorphic as an algebra to the ring of polynomials in elementary symmetric functions. In other words, if you have any symmetric polynomials in variables x1, xn, then you can always find some polynomial, just ordinary polynomial, which evaluated in variables e1, en, will give you geosymmetric polynomial. So we will prove this theorem later. For now, let me give just one example of its application. Well, just example why it's true. So suppose that you have some, let's take some symmetric polynomial, say x1 cubed plus x2 cubed. So how to understand that indeed it can be expressed through elementary symmetric functions? Well, it's very simple. You can write it x1 plus x2 cubed minus 3 x1 x1 x2 x1 plus x2. So you can see that this is e1 to the third power minus 3 e1 e2. So we see that at least for this polynomial this theorem holds. Okay. What we will really need is to define similar notion for the infinitely many variables. So we want to define algebra lambda, which will be algebra of symmetric polynomials in infinitely many variables. So let me explain what we mean by that. First, let us introduce some notations. Suppose that we have some sequence of non-negative integers, alpha, alpha 1, alpha 2, alpha 3, and so on, such that all coordinates are non-negative integers, and also assume that sum of these coordinates is finite. We will call such alpha multi-index, and given such alpha, we can always write a monomial x to the power alpha, which is simply x1 to the power alpha 1, x2 to the power alpha 2, and so on. Since sum of the alphas is finite, so alphas become 0 from some point, and it means that this is actually a finite product. Now we define the algebra of symmetric polynomials by the following simple definition. So we say that element of this algebra f is a power series in variables x1, x2, x3, and so on. So this element can be written as sum over all multi-indices, sum coefficients times monomials. And this sum should satisfy two properties. So first property is that this sum should have finite degree, which means that there exists some constant d such that if C alpha is non-zero, then sum of the alphas then sum of the alphas is at most d. So it just means that there is some finite degree series. And second condition is that this is symmetric series, which means that if you take C alpha and do some permutation of indices, then the coefficient should be the same. Okay, so let's put some examples of symmetric polynomials. So for instance, sum of all variables is symmetric polynomial in infinitely many variables. Sum of all variables. Then another example might be sum over all I and j y squared xj, say I is not equal to j. This is again symmetric polynomial However, if you consider something like that, product over all I 1 plus xi, then this is not symmetric polynomial because we don't have this first condition, because degree will be unbounded if you open the brackets here. Okay, so these are symmetric polynomials, and so lambda will be the ring of all symmetric polynomials. Again, we will want to consider some distinguished elements in this algebra. Well, first it is, well, one can prove that this is indeed algebra, so you can multiply and add these elements, so I will leave it without proof. I hope that everyone understands it. Now what we'll need is certain generators of this algebra, so certain specific symmetric polynomials. So first class of symmetric polynomial that we will need is again elementary symmetric functions. Well, their definition remains pretty much the same. Only here you remove the condition that all indices are less than n, and you arrive at elementary symmetric function in infinitely many variables. And it is also, this notation is given in the handout as formula number 1. Next thing that we need is so-called complete homogeneous symmetric functions. They are defined very similar to these ones. Sum xi1, xik. So these things are called complete homogeneous symmetric functions. Why they are complete we will understand in a second. Then there is another well-known family of symmetric functions which is a so-called family of power sums. They are denoted pk. Is just sum over all I xi to the k. So very simple definitions. And what we need actually, clearly these elements might be algebraic generators, but they don't span basis in our algebra. We want some elements which will span basis in our algebra. So all the natural bases will be parameterized by partitions. So let me tell what is a partition. If you have some number small n, then partition is just a collection of non-negative integers such the sum of these integers is n. As we will see, it's very natural to consider partitions in relation to symmetric polynomials. The first reason for that is that very natural basis is parameterized by these partitions. More explicitly, consider what is called monomial symmetric function. So what is monomial symmetric function? Well, this is just an analog of usual monomial in theory of usual polynomials. But when you want to make it symmetric, which means the following. So you take, so m lambda is the following. You take some monomial x to the power lambda 1, x2 to the power lambda 2, and so on. And then you try to find the most simplest symmetric polynomial which has this term. More formally, you consider the following thing. You say that m lambda is sum c alpha x to the alpha, and non-zero alphas is only those which are permutations of your lambdas. So you consider all permutations of this partition lambda, so permute indices however you want, sum over all remaining all resulting things, you get some monomial. So these coefficients are either 0 if that's not permutation, of 1 if alpha is permutation of lambda. So these are called monomial symmetric functions. Also, we will need another notation. So we will construct some more complicated elements after than pk, ek, and hk, which are the following. So if you again have any lambda, then we will denote P lambda will be just a product of all non-zero coordinates of lambda, P lambda y. In the same way, E lambda will be again similar product, and H lambda will be again the similar product. Okay, so these are basic definitions. So why are these guys called complete symmetric functions? It's very easy, because from the formula one can see that this thing is equal to the sum of all m lambda such that such that lambda is a partition of n. That's our notation for. So here, for the sum of lambda y, we will use the notations absolute value of lambda. So from the definition, one can see that indeed. So they are really complete. This is the sum of all symmetric functions of a given degree.
Just to understand, you write H2.
Yeah, sure. So H2. So let's say in two variables. Okay, that will be x1 squared plus x1 x2 plus x2 squared. That will be sum of all possible monomials of this degree. Okay, now next thing that we need is to find some relations between these elementary symmetric functions, complete homogeneous functions, and so on. So to find some relations between them, we will need to introduce some generating functions. Okay, so first is generating function for the elementary symmetric functions. It's usually denoted by big E of t. So this is just formal sum from 0 to infinity t to the k times ek. Again, we agree here that E0 is 1, so this series starts from 1. Now there is a formula for the generating function expressing it through our variables, which says that
monomial functions counted with some multiplicities or just
no. So all the coefficients here are either 1 or 0. So you can express it through variables in the following way. So this is just product of y 1 plus t xi. So this is our first theorem. So how to prove it? Well, just let's try to open the brackets here. So you have 1 plus tx1 times 1 plus tx2. So let's try to find coefficients of t to the k. So what we should do, we should take t from one bracket, t from some other bracket, and so on. So we should just choose the indices of these brackets. And now you look at the definition of elementary symmetric function and see that these are exactly these indices. And you exactly sum these variables. So this is the proof of this formula. Now for complete homogeneous functions, there is also formula. So in the similar way, we define h of t as sum t to the k hk. Then the formula is the following. This is product on y 1 divided y minus t xi. So this is the formula. Again, how to prove it? To prove it, we just need to use formula for geometric series. So rewrite 1 minus txi as 1 txi plus t squared xi squared, and so on. And then again open the brackets, and you will see that you get exactly this formula. Finally, for the power sums, we will consider a little bit modified generating function, which is the following. So P of t will be sum from k equal 1 to infinity pk t to the k divided by k. And again, this generating function has a simple formula, which is the following. P of t is minus sum over all I logarithm at 1 minus xit. So how to prove this formula? Well, basically you just use known Taylor decomposition of logarithm, and then you see that you get exactly this formula, just because pk, this is what is it? It's x1 to the k plus x2 to the k, and so on. And these are exactly the terms which appear in the Taylor decomposition. So this is the proof of this formula. Okay, now from these three formulas, you can immediately see that they're very much similar. So we can write down some relations between these formulas. So these relations are the following. First, what we see is that E of t times h of minus t is equal to 1. Just simply comparing these two formulas, we see that. The second similar formula is that h of t is equal to exponent of p of t. Again, just comparing these two formulas. So what are corollaries of these formulas? So now we can write down what are relations between elementary, complete homogeneous, and functions and power sums. For example, if you look at this formula and try to open the brackets and see what's happening there, then we arrive at the following formula. Let's sum from 0 to n hk times e n minus k times minus 1 to the power k is equal to 0 for any n at least 1. So this gives us some relations between complete homogeneous functions and elementary symmetric functions. Also, we can write down, from this relation, we can write down the following formula. N is equal to sum r equal 1 to n pr h n minus r. So how we obtain this formula? This is just by differentiating this statement. So if h of t is exponent, then h prime of t is p primes time exponent, which give us that h prime of t, h of t times p prime of t. And then this formula is just the manifestation of this. Okay, so these formulas are again given in the handout as formulas number 5 and 6. Okay, now we want to prove again the main, maybe fundamental theorem about symmetric functions. Which is the following statement. So lambda, the ring of symmetric functions, similar to the finitely many variables case, is again isomorphic to the algebra of polynomials. This can be written either as C of E1, E2, and so on, or C of H1, H2, so on, or C of P1, P2, and so on. So now we will try to prove this theorem. First, note that it is enough to prove only one of these formulas, simply because if you know that every symmetric polynomial is, say, polynomial in variables E, then we can immediately express it as polynomials in variables H just using these formulas. In the same way, we can express it as polynomial in variables P, so in power sums, again using these formulas. So it is enough to prove only one of these equalities. So we'll prove this one. So we'll prove that every symmetric polynomial is a polynomial in elementary symmetric functions. So that's our theorem. Let's try to prove it. Well, first, what we have is that any symmetric polynomial can be decomposed into sum of monomial symmetric functions. So any polynomial is some finite sum of some partitions of C lambda times monomial symmetric functions. Just because monomial symmetric functions are some basic blocks of all symmetric functions. So it means that it is enough to prove that any monomial symmetric function can be expressed as a polynomial in elementary symmetric functions. So how we will prove that? For that we need to introduce certain ordering on the partitions. So suppose that we have two partitions, lambda and mu. So we will define what does it mean that lambda is greater than mu. First we can compare partitions of which numbers are lambda and mu. So if the sum of the coordinates of lambda is greater than sum of the coordinates of mu, then we say that lambda is greater than mu. If these numbers are the same, so if lambda and mu are partitions of the same number, then we use a lexicographic order, which means the following. So if they are equal, then first we can compare first coordinates of lambda and mu. So these are largest coordinates. If lambda 1 is greater than mu 1, then we say that lambda is greater than mu. If lambda 1 is equal to mu 1, but lambda 2 is greater than mu 2, then again we say that lambda is greater than mu, and so on. This is lexicographic ordering on the partitions. So what is important for us is the following fact that if you take any, this is the property of this ordering, if you take any partition lambda, then the set of all partitions mu which are less than lambda is always finite. Well, in principle, this follows from these formulas. I will just show you one example. So suppose that you have, so lambda is partition 3 greater than 1, less than 0, and so on. So partition with just two parts, 3 and 1. So what are all the partitions which are smaller than that? Well, there are not many of those. So this is 2 greater than 2, then 2 greater than 1, greater than 1, greater than zeros, 1 greater than 1, greater than 1, greater than 1, zeros, and also all the partitions of degree less of the power or degree less than 4. So I won't write them down. Hope that everybody can do that. Okay, so we have this ordering. Now, another important thing for us is a graphical representation of this partition. So we will draw partition as a so-called Young diagram. So this is a collection of boxes So we put boxes in rows such that in first row we put exactly lambda 1 boxes. In second row we put lambda 2 boxes. In third row we put lambda 3 boxes, and so on. So for example, this picture, which is called Young diagram, corresponds to the partition 4 greater than 3 greater than 1 then zeros. And in particular, number of boxes is just sum of all coordinates, what we denoted modulus of lambda before. So this is Young diagram. Now there is another there is another parameterization of Young diagrams. So here we're looking at the row length of this picture, but we can also look at the column length of this picture. So let's write the columns of our Young diagrams, which we'll denote by the same letters lambda but with prime. So lambda prime, lambda 3 prime. So what are those for this picture? So the first coordinate is 3, second is 2, then again 2, then again 1. So this is 3 greater than 2, greater than 2, greater than 1, and then zeros. Now, with these notations in hand, we can see the following statement. That the product E lambda 1 prime, E lambda 2 prime, E lambda k prime, so k here is just number of columns in our Young diagram, is equal to the monomial symmetric function m lambda plus sum with some coefficients c mu and mu, but in this sum only partitions which are less than lambda come. So why is this true? Well, this actually follows from the definition. So how E lambda 1 looks like, E lambda 1 prime looks like? Well, it starts from x1, x2, x3, x lambda 1 prime, and then plus something else. How this one looks like? It again starts from the same thing, x1, x2, x lambda 2 prime, plus something else. Then when you multiply such things, so when you multiply such things, you can see that you are basically just building your Young diagrams out of columns. So this gives you first column, this gives you second column, and so on. So from this formula, just opening the brackets, you see this. Now the statement that monomial symmetric function m lambda is a polynomial of the elementary symmetric functions can be proven just by induction, just induction in this order that we introduced. Since we know that there is only finitely many preceders in these orders, we can use induction here. And so if we know already that these monomial symmetric functions are expressed as polynomials, then from this formula we also prove that m lambda is expressed. Okay, so this proves our theorem. Is it clear? Are there any questions about this proof? No, okay. So for now, we also need to relate symmetric functions in infinitely many variables to symmetric functions in finitely many variables. So this is done through the following map. So if you have some symmetric function in infinitely many variables, say f, x1, x2, and so on, then you can always specialize all variables except finitely many into zeros. So you map it to the f of x1, xn, and then zeros. So after substituting these zeros into formulas, you get something which is, as you can see, which is a symmetric function in variables x1, xn. And our basises, they behave good under these identifications. So, for example, ek in infinitely many variables is mapped to ek in finitely many variables as soon as k is not greater than n. So what it means is that this map is some algebraic homomorphism, which is also a bijection on the set of all polynomials of degree at most n. This simple observation has two important corollaries, which are like two principles how to work with symmetric polynomials. Let's write them down. So principle one is the following. If you want to prove some formula, some finite formula involving symmetric polynomials in infinitely many variables, then always it is enough to consider only a finite collection of variables as soon as the number of variables is large enough. This follows just because this is a bijection. So this is principle one. Enough to consider finitely many variables if this number is large enough. So second principle explains how can you define some new symmetric polynomials. This is the following. So suppose that you have a sequence of symmetric polynomials f1, f2, f3, and so on, such that degrees of f's are bounded, some number d. f1 is symmetric polynomial in one variable, f2 is symmetric polynomial in two variables, f3 is symmetric polynomial in three variables, and so on. And this sequence satisfies the following property, that if you take fk, put 0 as last variable, then you get fk minus 1. Then this sequence defines you a function of our ring of symmetric polynomials. So this is the same. So this again follows just from looking at this thing. So these two principles we will use intensively in working with symmetric polynomials. Okay, now what we need, next thing, maybe this is the most important definition of this TA session, is notion of so-called Schur polynomials. So principle 2 says that to define symmetric polynomial in infinitely many variables is the same as define a sequence of symmetric polynomials such that first polynomial has one variable, second polynomial has two variables, third polynomial has third variable, and so on. And this sequence satisfies two properties. First, degrees are bounded, and second, when you take kth polynomial, specialize the last variable to 0, then you should get k minus 1th polynomial. So these polynomials are just obtained by putting zeros for all variables except finite collection. Okay, so now we come to Schur polynomials. Okay, Schur polynomial. So definition of Schur polynomials is inspired by following idea. We considered symmetric polynomials, which are symmetric under permutation of variables, which means that x1, x2, xn is the same x1, so let's put here xy, So xy, xj, xn is the same as the result of permutation x1, xj, xy, xn. So this was the definition of symmetric polynomial. Another well-known class of polynomials is the skew-symmetric polynomials, which are polynomials which satisfy this property that when you interchange two variables, the sign of this polynomial changes. This is the definition of skew-symmetric polynomial. Skew-symmetric polynomial. So now, in the same way as monomial symmetric functions, we are spanning all symmetric polynomials, we can find skew-symmetric analog of monomial symmetric function, which in this case is written in the following way. So you take some monomial, x1 to the power alpha 1, xn to the power alpha n. Then you consider its what we'll call alternant of this monomial, which is defined as a sum of all permutations of n elements minus 1 to the number of inversions in this permutation times x sigma of 1 alpha 1 x sigma of n alpha n. In other words, you permute the variables in all possible ways, but also you collect signs. And one can prove that indeed this gives a skew-symmetric polynomial. Then the next observation is the following. So skew-symmetric polynomial, by the definition, satisfies the following property. If two variables are equal, then this polynomial is 0, which means that f xy xy is identical 0. So what does it mean? If you think about it, then you understand that it means that any skew-symmetric polynomial is divisible by xy minus xj. Because when xy is equal to xj, it's 0, then it's called Bézout theorem, says that it's divisible by xy minus xj. But this is also true for any pair of y and j, which means that any skew-symmetric polynomial can be divided by the product of all I less than j, x1 minus xj. So let's then take this alternant and divide it. So you take alternant x1 to the alpha 1, xn to the alpha n, divided by product xy minus xj. What you get is already some symmetric polynomial, because this part is skew-symmetric, this part is also skew-symmetric. It means that the ratio is symmetric polynomial. Now we see that it's enough to consider just decreasing subsequences, of course, but what we also can prove is that, so I'll leave it as exact exercise, is that one index is one of the parameters is equal to another. So if alpha y is equal to alpha j, then this ratio is just identical 0. It means that it is enough to consider only the sequences which are strictly decreasing, alpha 1 greater than alpha 2 greater than alpha n. Since we were dealing with partitions before, it is convenient to parameterize it again by partition, which is the same thing, but which strict inequalities replaced by not strict, by weak inequalities. To do that, we simply say that given lambda, we define alpha y to be equal to lambda I plus n minus I. So with this parameterization in hand, we get the definition of exactly sure polynomial. So this ratio of alternants is called sure polynomial, parameterized by partition lambda in variables x1, xn. So another way to write the same definition is the following. You can also write that as lambda of x1, xn is determinant xi to the power lambda j plus n minus j divided by product xi minus xj. So here the determinant is of size n times n, and determinant is the same as alternant just by the definition of determinant. So is the definition of sure polynomial clear? Okay. So for now, this is a polynomial just infinitely many variables. But from the definition, one can prove the property that if you specialize one variable in 0, xn 0, then you get the same sure polynomial as soon as the n plus 1th coordinate of your partition is 0. Which means that for any fixed partition, if we have large enough n, then we get exactly such a sequence, so that after substituting 0, you get previous element. It means that this sequence defines our polynomial. So it means that sure polynomial can be also viewed as polynomial in infinitely many variables, just defined in this way. Okay, so this is sure polynomial. Now, what we need next is very important identity about sure polynomials, which is usually called Cauchy identity. So let's state it. So this identity is somehow similar to the evaluation of generating functions for elementary complete symmetric functions and power sums. But for sure polynomials, it takes more complicated form. It says the following: the sum of all Young diagrams lambda, sure polynomial evaluated at x1, x2, and so on, times sure polynomial of other set of variables, i1, i2, and so on, is equal to the product of all I and j, 1 divided by 1 minus xi ij. So this identity is usually called Cauchy identity. It's also somewhere in the handout. So I think it's formula 14, yes. So now we will try to prove it. So this is a theorem. So the first thing that we need to prove is the following lemma, which is called Cauchy determinant. So lemma is the following: the determinant, so n times n determinant of the following thing is equal to product xy minus xj times product minus ij divided by product of all I and j xy plus ij. Okay, so how to prove such a determinant evaluation? The proof is the following. So let's multiply both parts by this denominator. Then in the left-hand side, you get these determinants times this product. Now, expanding just by the definition of determinant, you can look at the sum of some terms, and you can see that all the denominators will cancel out, and in the result, this product will be just a polynomial. So this product will be polynomial in xy and yj. Okay, now what is the degree of this polynomial? Well, here we had degree n, here we had degree n squared. So since it was in denominator it was minus n, here we had degree n squared. It means that after multiplication we will get the polynomial of degree n squared minus n. Now, now we see the following property. If xy is equal to xj, then this determinant has two equal rows, which means that it evaluates to 0. And also if iy is equal to ij, then it has two equal columns, which means that again it evaluates to 0. Then by the same argument as in defining sure functions, we see that with polynomial with this property should be divided by product of all xy minus xj over all I less than j, and by product of yy minus yj over all I less than j. Then look at the degree in this part. So this thing has degree n times n minus 1 over 2. This thing has degree n minus 1 over 2, which means that this product has exactly degree n squared minus n, which means that the left-hand side and right-hand side are equal up to some constant. Well, and to see this constant, just you can compute leading terms, say, in the left-hand side and right-hand side, and see that this is equal. So this proves this lemma. Now, now you can rewrite this lemma in the following way. You can write, so after some simple change of variables, you can write the determinant of 1 minus 1 minus xi ij is equal to, again, the same thing, psi minus xj, product y minus aj, and product 1 minus xi yj. So here you consider again the finite collection of variables, say n, and well, this is obtained from this just by change of variables yj to 1 minus ij and changing the signs. So this is the same identity, pretty much. And now we'll prove the Cauchy identity as was first principle was saying to us. It's enough to consider only finite collection of variables. So we'll consider n x's and n y's and try to prove the identity for these collections of variables. Then after using this identity, here we see exactly the right-hand side. All the things, and using definition of sure polynomials, all the things boils down to following identity. So sum alpha 1 greater than alpha 2 greater than alpha n, alternant of x1 to the alpha 1 xn to the alpha n times alternant of I1 to the alpha 1 yn to the alpha n is equal to the determinant 1 minus 1 xi ij. Okay, now how to prove this identity? Well, what we need here is actually definition. So, by the definition, left-hand side is equal to sum over all lambda 1 alpha n minus 1 power sigma tau, which again means just number of inversions in sigma tau times x sigma of 1 x tau of 1 alpha 1 sigma n alpha n x tau n alpha n. So this is left side. Now Now what can you observe? That this is indeed equal to sum over all alphas.
Why is it y to the power?
Yes. Thank you.
Excuse me, there is also a sum over the permutation.
Yes. Sum of all pairs of permutations. So this is actually equal to the sum over all alphas, sum of all sigmas, sine of sigma x1 sigma of 1 to the power alpha 1 xn y sigma of n to the power alpha n. So how to understand that this is identical? Well, first, here we had ordered variables, here we have unordered variables. It introduces n factorial, but in the same way you can observe that here actually everything was summed many, many times just because everything is symmetric. So with this remark, I will leave it as an exercise to prove that this is equal to this. This is just comparison by comparison of the terms. But then you can see that this sum is precisely this determinant as soon as we expand 1 minus xi xj as 1 plus xi ij psi ij squared plus so on. Then pretty much by the definition, this sum is the same as this determinant. So this gives us proof of the Cauchy identity, which is, as we've seen, the formula there. So what we also need, so let me write down again Cauchy identity, sum of all lambdas s lambda x1 so on, s lambda y1 and so on is product 1 minus 1 minus xi ij. What we'll need is also another expression for the same product of 1 minus xi ij. So this is the following expression. First, you can write it as exponent of sum k greater than 1 pk of variables x, pk variables y's divided by k. So why is this true? Well, look at the generating functions for the power sums. So exponent of generating functions of power sums is very similar product. Only you should consider the variables x, y over ij. But power sum in the variables xi, yj is just the product of power sum in variables x in x's times the power sum in y's. So then this evaluation is just identity of generating function for p functions. Also, you can open the brackets here and obtain the formula which is in the handout, I think formula number 13. I won't write it down on the blackboard, but you can prove the formula that sum over all partitions p lambda of x's times p lambda of y's times some mysterious constant, which is actually not very mysterious, it just comes from the exponent, is equal again to this product. Okay, now the last thing that I want to speak about today is the notion of specialization. So it is also given on page 2. Yes. I will give definition and then so specialization rho of algebra of symmetric functions is just some homomorphism of this algebra into complex numbers. So any such homomorphism is called specialization. Now we know that lambda is ring of polynomials in, say, variables e1, e2, and so on, or polynomials in variables h1, h2, and so on, or polynomials in variables p1, p2, and so on, which means, and we know that these things are actually algebraically independent, which means that to define this specialization, it's enough to define just values of this specialization on each of these generators of this algebra. So we can send E1 to arbitrary element, to some constant C1, E2 to some constant C2, E3 to some constant C3, and so on. And this constant can be chosen arbitrarily, and we will get some homomorphism of these lambda to the complex numbers. Now let me give one important example of this specialization. Well, you can recall that these are polynomials in principle. It means that you can just put the variables and just compute. So these are some power sums. So you can always this is some polynomial of x1, x2, and so on. Then you can just evaluate it. So substitute some numbers, say c1, cn, and then all zeros. So you just substitute it as a power series, as a sum. Just evaluate, so you will get some convergent power series. You evaluate anything, get some limit, and get something. And one can prove that this will be specialization. So this is some kind of very simple specialization, where you, just as the meaning of the word, you specialize the variables. But in general, specialization is might be much more complicated, which we will see in the future, in the next lecture, I think. And it can be defined by any sequence of constants. Okay, let me stop here on